Hello, and welcome back to the video lecture series for Introduction to the Art of Programming using Scala. In this video, we're going to finish off the stack implementation that we started 2 videos ago. In our last video, we wrote some unit tests, and we found that while the first 3 unit tests that we wrote to make sure that a new stack was empty, push a single element, check that it was not empty, push 3 elements, pop the 3 elements, make sure they came off in reverse order, and that it ended up empty. Those all worked. But then we wrote one that had to push 100 objects onto the stack and then pull them off in reverse order, and it failed because it threw an exception. And the reason it threw an exception is because we have an array that is all of 10 elements in size. Okay, so that's our problem. How do we fix that? Well, if we push something and it's not going to fit on the array, we need to make a bigger array. Okay, so we'll start off if top is greater than or equal to data.length. Okay. That means that we don't have space to put this. So what do we need to do? We need to make a bigger array. And then we're going to have to copy things over and then make that new bigger array into the array that we're using. So I'll create an array, I'll call it temp. Is a new array of type A, and the question is, how big should this array be? Okay, how big do we want this? Well, it's tempting to do something like data.length plus 10, or maybe plus 100, or whatever. Okay. That's a very tempting thing to do, and I think that a lot of novice programmers would choose to do exactly this. There's one problem with this, though. If you go back to a few videos, I talked about order notation because I have one requirement on all of my operations here, and that is that they have to be order 1. Okay. I need to make it so that no matter how many elements are on the stack, these things are going to take a fixed amount of time. Now, we'll talk about the fact that this is kind of an on average thing. This peak clearly it happens the same whether you have 10 items or 10 million items. Same thing for isEmpty. Same thing for pop. And what we had for push did this too. But now I'm going to do something here. So we'll just leave that at plus 10 and then we'll come back and think about this a little bit. What's the next step in here? Well, the next step is something like for I in data.indices temp sub I equals data sub I. So I copy those elements over, data sub I, or sorry, just data equals temp. That's unhappy because right now our data is a val. Clearly we're going to have to make it a var because we have to be able to change what array we're using. Okay, so this for loop right here is not order 1. Okay. This for loop right here is order in because I have to run through all of the in elements that were in my data array and copy them over. And that is problematic. Okay, how can we get around this? Well, in some ways, I can't. What I'm going to do instead is I want to make it so this doesn't happen often, so that the way it works out is if I add in elements, I only copy in elements, and so on average I'm only doing 1 copy per push. And so now granted all those copies will be lumped into a single time, but as long as it all averages out to order 1, I'm happy. This way of doing things does not average out to order 1. Okay. I put on 10, and then as soon as I've pushed 10 more things, I have to do it again and again and again. Turns out that if you grow by any fixed constant, the amount of work that you're going to do is going to be order in, even when you average it out. Which means that when you push n items, you're going to take order n squared time to do it. And I want to make it so if I push in items, I take order n time to do it. Because if I do something that's order 1 n times, the result is order n. So how can I do this? How can I make it so that the number of times that I have to do this copying goes down such that the number of copies that I make winds up scaling as n? And a simple way to do this is to not change the size by an additive factor, but to change it by a multiplicative factor. So an easy way to do this is to just say times 2. Okay. Now why does this work? Well, this works because let's pick some, pick some number like 32. If I had multiplied by 2 multiple times, I get to 32. 32 plus 16 plus 8 plus 4 plus 2 plus 1 happens to be equal to 2 times 32 minus 1. And it turns out whatever power of 2 I stick in here, this is going to work. So I have a constant multiple of that power of 2 minus 1. You might also know this as the mathematical relationship 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, etc., equals 2. Okay, so it's an infinite sum of values, but they wind up all adding up to the nice value of 2. Same type of thing happens here. Because this grows by a factor of 2 each time, the number of times that I have to do this copy operation goes down logarithmically. And so on average, when you add up all of my copies, it will wind up adding up to basically 2 times the number of things that I've pushed on, which is still order 1. And that's what we were going for there. So now that I've written that, question is, does it work? Well, we can come back over here to our test, and I can run my test and a green bar. Okay, so it passes this last test. Viewers are strongly encouraged to come up with other tests of their own to make sure that what we're doing. One thing I would note, I have not made a single test call to peek in this. Okay, I could do that fairly easily by doing an assert equals of in and stack dot peek before I do the pop, and of course our peek works nicely. But you could add more tests onto this because in many ways this isn't complete. I do things like I push and then I pop. I never did a push a bunch of things, pop a bunch of things until empty, and then push some more on. There are actually bugs in certain ways of writing these data structures, not so much for the array stack, but things that we'll see, where emptying it all the way and then re-pushing can show you that you had an error, where if you don't do that type of test, you won't see it. This is sufficient for our purposes, though. We now have a working array-based stack, and so we're going to leave the stack. In the next video, we're going to come back and we're going to implement our queue interface and write an array-based queue.